Hey guys, hi, this is Radhakrishna and this video is about Aristotle's wheel paradox, and basically this video is going to be a reply and a little more explanation on a video that is posted by Up and Atom, this particular video. So in this video it's a clear description of what Aristotle's wheel paradox is and why the paradox actually comes into play and what is the exact reason. I request you all to first see this video or any other video which describes Aristotle's wheel paradox first. It's nothing complicated, it's just a question asking why do two concentric circles, when they are moving on a straight line, actually represent the same amount of traverse length of a particular bottom point. It's not very complicated at all. If you see the diagram, you will understand what the paradox is. Now in this particular video that Up and Atom has done, there's a slight mistake that they have done. So she has shown a very beautiful depiction of how Galileo had tried to estimate why this is happening, and it's for a matter, it's true that what Galileo estimated is the exact reason of why it is happening, right? So the basic reason, if you don't want to me to spoil, you go and watch the Aristotle Wheel paradox and then come and watch this right now. So the basic reason why this paradox happens is because of slipping, and slipping also not exactly slipping, but there's a motion difference between two concentric rings that if you take and analyze, right? So if you're taking exact rolling without slipping of the outer disk, and the inner disk, all of the inner disk will be having slipping, right? So if you're taking rolling without disk on the outermost disk, all the inner disks will be having slipping, and the conflict here is basically how do we understand slipping as a concept, right? So that's the most important thing. Now I will just show you this video, and you can see that what she is telling at this particular point at 3 minutes 55 seconds. Sorry, yeah.
He concluded that the inner circle must be making an infinite number of skips. While Galileo wasn't exactly right, it does get us closer to...
I hope you have seen what is shown in that video. So Galileo has taken regular polygons as n increases slightly, and slowly he tried to approximate it to a circle. So initially he tried it with pentagon, then hexagon, and then octagon, and so on and so forth, and he tried to estimate what are the skip distance between different points, right? What is the skip distance between different points. Alright guys, so I'm going to show you a little of my analysis on this particular problem. This is basic physics, nothing but rotation, translation, slipping, rolling basically. So most of it is going to be mathematical, so, and it's also simple as well. I want to basically convert this to the Galilean explanation that Up and Atom channel has put down. So first off, let's take a basic circle or a disk which is rotating. There's no rolling here, just rotating. So the rotating locus is basically going to be a circle, right? So let's just say it's r cos theta, r sin theta, but here theta is with respect to x-axis, the locus of a circle. But when we consider rotation, we can just take with the negative y-axis, and then the theta is going to be pi plus 90 minus theta. So it's going to be minus r sin theta minus r cos theta, which is also a circle again. Now this is basic rotation. This is the point locus of this particular point is going to be a circle. Now when we add translation, then basically when we say translation, then that means the whole body is moving. In rotation it's not moving, it's rotating. But when we say translation is also happening, that means the whole body is itself as moving. That means there's some velocity for the center of mass, right? So let's just say that the velocity of center of mass is some v, right? And then there's also rotation, so the whole body is moving. So then that is called as rolling. The whole body is rotating and translating. Now when we say slipping, right, then when we say there's no slipping, that means this point, right, effectively this point, the effective velocity is 0, right? So then there's no slipping. This point actually has no velocity, right? So for that to happen, the tangential velocity over here has to be equal to the translational velocity as well, right? So the tangential velocity over here is r omega, where omega is the angular velocity. When that is equal to the translational velocity of the whole body, the moment at this point is going to be 0, and the moment over here is basically the translational velocity, which is r omega, and here in the both of them are going to be in the same direction, which is 2r omega, and the whole body itself rolls, but there's no slippage, right? There's no slippage. So that's the whole concept here. So when we add the translational motion with the rotational translation velocity, so what we have basically here is the velocity, right? Vc, right, into t is the locus of this point, and basically the whole concept of this video is to find the locus of this point, right? So the velocity, the effective velocity of any point in this cylinder is or whatever it is basically the translation velocity is also there, and at the same time we also have what? We also have the rotational velocity, the translation velocity, and also the tangential velocity, which is rotational velocity. So combinedly we already have a component of x-axis, right, which is minus r sine theta, right? So that is the rotational thing, right? To that we are going to add a bias term. This is vct, which is translation velocity of the whole body, right? So when we add a bias term to that, what we have finally is r omega t, which is translation velocity of the whole body, minus r sin omega t, which r can be anything, right? This capital R is the whole, the radius of the whole body of the disk, and this r can be anything, right? This r can be whatever we are trying to measure for. So this radius, if it is equal to capital R, then this is the locus of the bottommost point, right? So that's what I also put in the calculator in the graph. That's what I want to show. So this is the equation here. The x-axis, the x coordinates are basically let's just say t is the omega t or something, and k is the ratio of the radiuses. This is small r by capital R, and 1 minus cos t is the y-axis, and y-axis is anyways not so important. So so this k basically is the ratio of the radiuses. So initially, let's just say we are trying to measure for the bottommost point. So when we are able to see this, this is basically the cycloid motion that in the video she has also described. But when we take smaller radiuses, let's just say we are taking 0.5, which is half of the radius of the bottommost point, what we are able to see is the slippage, right? So this is slippage where the point is moving, but then there's slippage, there's the difference here, and then again the point is moving again. This is not exactly cycloid. This is t minus k sine t, where k is not 1 exactly, right? So this is the whole explanation what she has given. But what Galileo said is also exactly this, the same thing what has been described here. So that's what I want to show you all. So let's just take the case of a square, okay? And when we rotate a square, we rotate it by this point, and the whole side transforms to this again, another the whole square rotates again, and the another square forms here, right? So when we sort of try to measure the distance, or the distance between point this one and again the square, this chota square, the small square is going to rotate, right? And again there's the small square that's going to form here, right? So this is the new point, new right bottom point of the small square. Initially, only if the small square has rotated, this point should ideally be here with this, and distance between this point and the new point should be b, right? But when we actually measure with respect to some calculations, what we measure is the distance is basically a, which is the side of the square. The distance is basically a, right? The side of the square. At the same time, when you do the rotation so that this point comes back here again, the distance between this point, and again after 4 rotations where the square is going to be there is going to be 4a, right? This is the same thing as the Aristotle's paradox. Now the whole point of slippage here is you need to understand that the whole rotation is happening about this particular corner or this particular corner, right? So when we rotate about this particular corner, this point is actually not stationary, this point is actually moving, right? So this point moves like this with this as center and this as radius. This point moves, right? So that again it forms. Now we can actually estimate that this rotation and the degree of moving or the distance of movement for a n-sided polygon, general polygon, right? So I've taken a pentagon here, and this is a smaller pentagon, this is the larger pentagon, and once it rotates it is going to form a new pentagon, and we want to find out the distance between this point and this point, right? So what is basically the distance between this point and this point is what the distance is when we sort of try to measure, right? We get that the distance is a for any number, right? For any number of sides. So I sort of tried to find out the distance, and this formula is 2r into sine of pi by n, where n is the number of sides. Okay, and how do we find out this particular distance? It's very easy to find out this distance. So initially we need to I'll just give you the procedure, and then you can sort of try to find out what is going to happen, right? It's nothing complicated, it's very simple. So we have a radius, one line segment here, and it is getting rotated about this point with respect to some angle, right? And what is this angle? Angle is basically the exterior angle, okay, of this any particular polygon. So you rotate a line segment with respect to exterior angle, and you need to find out the length of the chord. This length of the chord c, this is going to be 2c, right? So using small length of the chord formula itself, we have the distance is 2r into sine pi by n. But the most important thing is we have to find out what is this length of the radius r for any particular regular polygon, right? So for that, if we know what is the height of this particular line segment, and if we know what is this distance, it's easy to find out this r. This distance is basically easy. So this is a, this is b, and when you subtract, we'll get this particular distance, and as the regular polygon is symmetric, this is going to be a minus b by 2. So this we know that it is a minus b by 2. What is the height? That's what we have to find out, and that is simple as well. So when you take a particular regular polygon and you have a centroid, so you divide it, and the angle is going to be 2 pi by n, because there are n triangles. You divide it, it's going to be 2 pi by n, and when you bisect this triangle, the angle is going to be pi by n, and then you do tan pi by n is basically a by 2 by height, right? So this is basically a by 2 by height, and then you have the height of bigger pentagon is, or bigger polygon is, a by 2 by tan pi by n, hb you have, and you want to find out the difference between these two heights, so as to effectively find out what is the height, the difference between the heights of two polygons. You have h is a minus b by tan 2 pi by n, and then you find out the radius, this particular radius that we are sort of trying to measure, this particular radius. So we have r is root of h square 2 pi by n, and r is basically a minus b by 2 into sine pi by n, right? So we substitute that into this particular formula again, and you sort of find out that d, the distance, is always a minus b, right? So it is basically showing that once this smaller pentagon is rotated, right? Again I will, this is rotated pentagon, for example, this point's difference between this and this is a minus b, right? The difference between this and this is a minus b, and this is again the side is going to be b, so the total difference between this and this, again effectively this this point and this point is going to be a minus b plus b, which is effectively a. So whatever you take, whatever you do, it is going to be a. And this is a simple explanation. It is very easy to understand from straightforward this thing also, because always it's going to be shifted by a and a and a. So all the points are internally going to be shifted by a. So there is always a slippage, and the amount of slippage is always a minus b. Whatever you take, whether it is n-sided polygon or infinite sided polygon, which is circle, whatever you do, whatever you take, it is going to be a minus b. And in the circle's case, because one thing is, if we are having the a coming back again towards the same point, that is the square or the pentagon completing its full rotation, this is basically going to be d is equal to n into a minus b, because there are n number of rotations that are required, right? So effectively this is the slippage, right? And the distance between point B and point B, again when this total polygon is rotated completely full one rotation, is basically n into a, right? So this is the perimeter of the particular polygon, the regular polygon, right? So in the same way, for the circle it's going to be 2 pi r. So this any regular polygon will travel this much amount of distance, but it had to travel only 2 pi small r if there were no slippage for the concentric internal circle or internal circle, right? So the difference or the slippage is 2 pi capital R minus 2 pi small r, which is effectively what is shown by Galileo's method. Galileo has told you exactly the same. This is the whole mathematics of slippage, right? So whatever you are seeing in the graph and whatever Galileo has told is exactly the same. So that's what I wanted to tell you. It's not something that has modern solution. It is already solved in 18th century.